and welcome. This lecture is devoted to a bunch of examples where I will derive both the MME and the ML estimator. Okay, so the method of moments estimator and the ML estimator for different problems and show you the similarities, differences and sort of illustrate how these things look and how they can be different, etc. Okay, let's start with the exponential distribution, and for the exponential distribution lambda hat MME is already known, if you remember, n by x1 plus xn. Okay, so this we have seen before, derived before, so you know this. How do we do ML distribution? Remember the PDF is lambda e power minus lambda x for x greater than 0, that is okay. Okay. So the likelihood is going to be product I equals 1 to n lambda e power minus lambda xi, okay, and let us simplify, I will multiply this together, you get lambda power n e power minus lambda x1 plus so on till xn. Okay, it is turning out to be easy enough, right? So how do we do this? You take log, so your lambda star is going to be argument of maximum over lambda, log of this is going to be n times log lambda minus lambda x1 plus xn. Okay. So now how do you do this? You differentiate and equate this to 0, you are going to get n by lambda minus x1 plus xn equals 0. So from here you get lambda star is just n by x1 plus xn. So from here you get lambda hat maximum likelihood is also the same guy, n by x1 plus xn. Simple recipe, isn't it? It's really simple, and we know it's got the distribution is very simply described as lambda e power minus lambda. You plug it in, you do the same calculation, you'll get to the answer. Okay. So here again we got both method of moments estimator and the ML estimator to agree. So that seems like a nice result to have. So this is easy enough distribution. Okay, so we're going to first start seeing some slightly non-trivial cases now. Okay, so the first case is a discrete case where instead of having 0, 1, just 2 values, I'm going to have 3 values. What are the 3 values? 1, 2, 3. So the distribution takes, the samples are either 1 or 2 or 3, 1 with probability P1, 2 with probability P2, 3 with probability P3. So the first thing I want you to note is P3 is going to be 1 minus P1 minus P2, right? Because the 3 of them have to add up to 1. They all will be between 0 and 1. Okay, so this will be true. Okay, so this is x1 to xn. So so let's do MME first. We'll do MME on the left side and ML on the right side. We'll do MME first. So if you look at MME, I'm going to have two equations. The sample moment M1 is going to be equal to expected value of x. Expected value of x is P1 plus 2P2 plus 3P3. This is one equation. The other equation is M2 is going to be the second moment, which is P1 plus 4P2 plus 9P3. Okay, so those are the two equations. Now I have to solve for the unknown parameters. So remember, these are the 3 parameters that are unknown. Okay. So because of this equation, I will take P1 and P2 to be the unknown parameters. Hope that was clear. I think I didn't say that early enough. P1 and P2 are the unknown parameters I have to find. So here I can substitute P3 equals 1 minus P1 minus P2. So these two equations will become, so if you put P3 equals 1 minus P1 minus P2, I'm going to get M1 equals P1 plus 2P2 plus 3 minus 3P1 minus 3P2, right? So if you simplify that, I'm going to get 3 minus 2P1 minus P2. Okay. So you can rewrite this, you can write 2P1 plus P2. I got this right. Okay, equals 3 minus M1. Okay, I hope this seems easy enough. So instead of P3, I'm going to put 1 minus P1 minus P2. So I got 3 minus 3P1 minus 3P2. So that's 3 minus 2P1 minus P2. So 2P1 plus P2 is this. Okay. So the next equation is M2 equals P1 plus 4P2 plus 9 minus 9P1 minus 9P2. So that's the same as 9 minus 8P1 minus 5P2. Okay, I think this is okay. If you rewrite this, you're going to get 8P1 plus 5P2 equals 9 minus M2. Okay. So this is one equation. The second equation, you're going to solve these two equations. Okay. So for doing that, you can multiply this first equation by 5, and then you can subtract that minus this. So you're going to get 2P1. So you can do 5 times 1 minus 2. This will give you 2P1 equals 5 times this is 15 minus 5M1 minus 9. So that's 6 minus 5M1 plus M2. Oh no, yeah, plus M2. That's correct. Okay. So this is what it is. So you solve for P1. So P1 is just 6 minus 5 M1 by 2 plus M2 by 2. Okay, something you got in terms of P1. So what is P2? P2 is, maybe I should write it somewhere here so that I can get more space. P2 is, you can put it here, 3 minus M1 minus 2P1. So that's minus 6 plus 5M1 minus M2. I hope I didn't make any mistakes in the simplification. It can be very painful otherwise. 4M1 minus M2 minus 3. Okay. So let me just check this real quick. If I do 2P1 plus P2, what do I get? 2P1 plus P2. Oh, I know where I made a mistake. This has to be 3. Okay, so okay. Apologies. I think I caught the error here. So if you do 2P1 plus P2, I'm going to get 3, and then minus M1 and M2 will cancel. So that's good. That's good. That agrees. And then 8P1 plus 5P2, what will happen? Okay. 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 I think it's okay. So this is correct. So from here, I've got P1 and P2 in terms of M1 and M2. So when I go back and find my estimator, P1 hat MME is going to be what? It's going to be 3 minus 5 by 2 capital M1 plus M2 by 2. Okay, and then P hat 2 MME is going to be 4 capital M1 minus capital M2 minus 3. Okay. So this is my MME estimator. So it required some work, but hopefully you're convinced it's not too difficult work, just setting up those equations and painfully solving for them. Okay. So what is M1 and M2? You remember what M1 and M2 are, right? So M1 is just the sample mean, right, x bar, and then M2 is just the second order, second moment, right, summation I equals 1 to n xi squared. So that's sample mean is just summation 1 by n summation I equals 1 to n xi. Okay, so I've expressed my both the MME estimators, some complex functions of no, not complex, just linear functions of M1 and M2. That's good enough to get. Okay, so how will ML look for this case? Okay, so notice this case is becoming slightly more involved than we thought, but ML actually happens to be very, very easy. Okay, so if you find the likelihood, this will be P1 power W1, P2 power W2, and then P3 which is actually 1 minus P1 minus P2 power n minus W1 minus W2. What is W1? W1 is number of ones. W2 is number of twos. Okay. So likelihood is really easy. So if you take log and differentiate, you're going to get P1 star, P2 star to be argument max over P1, P2 log of these guys. So it's going to be W1 log P1 plus W2 log P2 plus n minus W1 minus W2 log 1 minus P1 minus P2. Okay. So you can do this, you can differentiate. Now if you differentiate, you will see, you will get these very, very elegant and nice answers that P1 hat ML is actually equal to, no, let me just write the P1 star and P2 star. P1 star is actually W1 by n, P2 star is actually W2 by n. Okay. So notice how nice the P1 hat ML is. Okay. Number of ones in the sample divided by n. P2 hat ML is number of twos in the sample divided by n. Such simple, elegant expressions, a very nice extension of Bernoulli. In Bernoulli, this is what happened, right? P was simply the number of ones divided by n, W by n, okay? So we expect something like that when we do 1, 2, 3, P1, P2, P3. P1 should be the number of ones by n, P2 should be the number of twos by n, right? So that's the, seems like a reasonable estimator, but look at what the method of moments gave you. It gave you something really convoluted and maybe confusing. But you know, the ML decoder has given you very nice answers, very intuitively pleasing answers. So hopefully this gives you a comparison. Even though the ML decoder may seem a little bit more difficult in the beginning, the MME maybe is a bit more easy. The ML decoder gives very, very interesting answers in many cases. Okay, so in this particular case, it's very, very interesting. You can actually extend it to any number of digits. Instead of just 1, 2, 3, you can have 1, 2, 3, 4 up to something. You know that's something, and each of these probabilities you don't know. If you find a sample, the ML estimate of each probability of a particular letter in the alphabet is number of times the letter occurred divided by n. Okay, so this is a good principle to remember. It's easy proof in some sense. Okay, so hopefully, I mean, I didn't show you the differentiation. You can treat P2 as a constant and differentiate with respect to P1. You'll get this answers. Okay, it will need a little bit of work, but you'll get that. Okay. Next, we move on to another very, very interesting and simple looking case where you will get different answers with method of moments and ML. In this case, both are nice and simple sounding optimization problems, but you'll see the answer is very different. Later on, we'll come back and compare these two as well. Okay, so IID uniform 0 to theta, it's a continuous random variable, and the density, as you know, is 1 by theta for x between 0 and theta. 0 otherwise. Okay, this 0 otherwise is very important. Okay, keep that in mind. So let's start with the method of moments estimator. This is usually the easiest. Okay, M1 you can equate to the expected value of x. Expected value of x is theta by 2. From here you get just theta equals 2 M1. So theta hat MME is just 2 times M1, which is 2 times, you know, x1 plus xn divided by n. Okay. So the method of moments estimator is like trivial. It's 2 times x bar. It's another way to write it. It's 2 times x bar. 2 times the sample mean. Okay. Very, very easy estimator with method of moments. So again, is it intuitive? You know, you are expecting uniform distribution between 0 and theta. The mean is theta by 2. You compute the mean. You multiply by 2. Right. Seems reasonable. Okay. Let's see what ML says. ML will tell you a completely different story. Let's see what ML says. ML, the likelihood, so supposing you observe samples x1 to xn, okay, the likelihood of these samples is what? What is it? It's very, very interesting. There are two cases here. Okay. It is going to be 1 by theta power n, okay, if what? If all these guys lie between 0 and theta. It will become 0 otherwise. So let me give you a simple example of actual samples here. So here is n equals 3 and maybe you got samples like half, 8, okay, I'm taking an extreme example. So if you look at theta hat MME, the estimate is going to be half plus 8 by 3 into 2. So that's 9 by 3 into 2, that's 6, okay. So this is your theta hat MME, and notice 8 is bigger than 6, okay. So this actually gave you a estimate for theta with which the sample itself cannot agree, right. See, 8 cannot be obtained if you say the theta hat is 6, seems a little bit ridiculous, okay. So, but that is what the method of moments estimator is giving you. But on the other hand, if you were to maximize the likelihood, you have to absolutely avoid this, okay. To maximize likelihood, to maximize L, we have to avoid 0. Why should you avoid 0? 0 is really low, it cannot be maximum. I mean, a non-zero value is always bigger than a 0 value, right. So you have to pick a theta so that this condition is satisfied. So theta has to be above the largest xn that you saw, okay. So that's one condition we'll assume. So our theta star, we will say, is bigger than or equal to max of x1 to xn, okay. So this, once you do this, then your your theta will always be 1 by theta per n, okay. So the 0 won't occur, okay. So this kind of ridiculous, the method of moments, you're getting this case where you're predicting something which disagrees with the samples in some sense, right. So it's not a very nice estimator in that sense. So this maximum likelihood estimator is trying to avoid that, okay. So you're going to pick theta star to be greater than or equal to this, okay, and you're trying to maximize 1 by, theta to be greater than 1 by theta power n, okay, okay, and theta you're going to make it greater than or equal to this, so that this 0 doesn't occur. I'll always have 1 by theta per n. Now if I want to maximize over theta 1 by theta per something, I have to pick the least possible theta, right. Because if I keep increasing theta, my 1 by theta per n will keep on decreasing. So I have to pick the least possible theta, and theta is greater than or equal to max of x1 per xn. So clearly my theta hat has to be equal to maximum of x1 through xn, okay. So this is the ML estimator for uniform 0 theta, okay. So notice how the method of moments estimator disagrees so seriously with the ML estimator, right. It's 2 times sample mean is what the method of moments is telling you. The ML estimator is saying you observe n samples from uniform 0 theta, you don't know theta. What is your maximum likelihood estimate for theta? Maximum of the observed samples. That maximizes the likelihood, okay. You predict any theta inside the maximum, your likelihood is 0. Why will you ever predict that? Okay, it doesn't make sense. So you have to predict theta hat ML to be max of these. So in this case, theta hat ML will be equal to 8. You'll predict 8, you won't predict 6 like the MME estimator is doing, okay. So notice how the two estimators are so different. They're different in philosophy, but max of x1 comma xn is a very reasonable way to understand the distribution of make a prediction for uniform 0 theta, right. So you don't know theta, you're observing a lot of things. What will be the best prediction for theta? Maximum of those values. Very reasonable. It ends up being the maximum likelihood estimate, okay. So interesting example. So let's keep proceeding. So I don't know if you're the type who enjoys these kind of nice mathematical arguments and getting to the answer, but even if you don't enjoy the argument, look at the final expression, right. The final expression is a very intuitive expression for what the estimator can be for uniform 0 theta. So hopefully that is a bit more interesting for everybody. Okay, so next is a discrete distribution, uniform discrete distribution. I don't know n, okay. So here also you can do MME, you can do ML, okay. So I'm going to give you the final answer for ML. You can guess, it's not so difficult. max of x1 to xn. Okay, I am not going to prove this with great detail. You can see, you observe a lot of samples. It's going to be 1 by n raised to the power number of samples. You want to keep n bigger than the maximum that you observed, and you want to maximize the likelihood. You pick n as the least possible value that you can assign to do that. Okay, what will be MME? What is the expected value? It is, it's uniform, so it is 1 by n times 1 plus 1 by n times 2 plus so on till 1 by n times n, and that is the summation 1 times 1 plus 2 plus n, and that is 1 by n times n plus 1 by 2. Okay, you might have already known this. It's going to be n plus 1 by 2. This will cancel and you will get n plus 1 by 2. You can solve for them. You will get n equals 2 m1 minus 1. So, n hat MME is 2 times x bar minus 1. So, it's sort of related to 2x bar, 2 times x bar minus 1. It's sort of similar. Okay. So, you see again it's very different in the uniform 1 to n case. The method of moments estimator and the ML estimator are very, very different. Okay. Okay. So far we have seen cases where I was able to give a closed form expression for the ML distribution. So now we will see a couple of cases where we will not get closed form expressions. We will get some equations and I will say you have to solve it numerically. Okay. So the method of moments estimator we have seen before. I am not going to reproduce it here. You can go back to the one of the previous lectures and look at the slides. The method of moments estimator for the gamma distribution is derived there. Let us look at ML. So the likelihood is product I equals 1 to n beta power alpha by gamma alpha alpha times x power alpha minus 1 e power minus beta x. Okay. So if you want to simplify this, it's going to be beta power n alpha by gamma of alpha power n. You can't throw any of these out because they all depend on alpha, beta and all these cases you don't know, right? And then you have xi, sorry I forgot about the xi. It's xi, the product is going to come here, so you're going to get x1 till xn, whole thing raised to the power alpha minus 1, then you will get e power minus beta x1 plus xn. Okay. And alpha star comma beta star is argument maximization over alpha beta log of this. Okay. So if you take log of this, you're going to get n alpha log beta minus n log gamma of alpha plus alpha minus 1 log of product. Okay. Minus beta times, here maybe I can use the summation I equals 1 to n notation. Okay. So I took log, you can take log of each term and keep doing the subtraction or addition depending on how it works out. So you get this complicated looking expression. So now I am going to differentiate with respect to beta. Okay. So if you do that, so remember when you do that you can treat alpha and all as a constant. So if you do that, I am going to treat alpha as a constant, so it's n alpha times 1 by beta. Alpha as a constant, so this term will go away, alpha as a constant, that term will go away. Here you will get minus summation I equals 1 to n xi equals 0. Okay. So notice here this equation is nothing but alpha equals beta times the sample mean, right. So summation I equals 1 to n xi divided by n. Okay. It's a very nice relationship. We know alpha by beta has to be equal to the mean. So alpha by beta ends up being the sample mean as well. Okay. Nice intuitive relationship that needs to be satisfied by alpha star beta star. Okay. So the other one, it turns out you won't get anything so nice. It will be one very nasty looking relationship. You will get n log beta, okay, minus n by gamma of alpha. I mean, I don't know how many of you know this function, gamma function. It's a bit of a nasty function. It's maybe not that nasty, but it's a complicated function. It's not very easy to write down. Plus log the product, and minus 0 equals 0. So here you get this more complicated sort of equation. and alpha is beta times the summation. So these two equations together you have to solve, okay. And maybe you can rewrite this a little bit. This is maybe if you want, I'll rewrite it for you. You got to get. I'll write down log of product as sum of logs. Okay, so this term is the same. I'll get a divided by n here, and then I will equate it to push this to that side. I'll get gamma prime of alpha by gamma of alpha minus log beta. Okay, so I just divided by n to get a form sort of similar to that. So anyway, it doesn't matter how you simplify this. So these two you have to numerically solve. Okay, so there's no way to write a very clean closed form expression here. Okay, so there are computational procedures. You input this equation in some form into a Python program suitably with load some packages. It will solve and give you the answer. Okay, so this is the first case where we are not getting a very convenient, neat and clean closed form expression for the ML distributor. On the other hand, the method of moments estimator was very easy, right? It gave you a closed form expression in terms of the sample moments. So here we are not getting that. This log of xi and all is involved. It's not clear how it's going to work out at the end, but the ML, it's not very hard. Today, I mean, even the closed form expression, even if it is not there, solving these kind of equations is not very, very hard. One can put it into a computer and it will crank a little bit and give you the answer. Okay, so it's possible to do this. Okay. So there are many more examples like this, but the gamma is complicated enough for you to see. So once again, in this class, we won't bother too much about complicated problem solving like this. Even if we do this, we'll expect you to do some very simple differentiations only, nothing more than that. Okay. So the next example is binomial NP. Okay. So you remember MME we've seen before, so I'm not going to redo this. You can go back and check. Okay. So the ML, when you don't know both N and P, it becomes a little bit more complicated. So let's just see how the likelihood is going to work. The likelihood is going to be product I equals 1 to n, and choose xi, p power xi, 1 minus p power n minus xi, isn't it? Okay. So this is a bit complicated. It's not that easy. So if you take this, you can sort of start simplifying this if you like. You're going to get one term which will be like this: n choose x1, n choose xn, and then you will get p power x1 plus xn, and then 1 minus p power n times n minus this summation, right? So I hope you can work this out. So it's just this product multiplied n times, so you're going to get 1 minus p power n times n minus this x1 plus 1 till xn. Okay, so this is the expression that you get. It's a bit ugly, I agree. You can take log now. Okay, so just to take log, sometimes it's useful to take log like this and see how it works out. So you're going to get log and choose x1 plus so on till log and choose xn, right, plus x1 plus xn log p plus n times n minus x1 plus xn log 1 minus p equals 0. Okay, you're going to get this. Okay, so you can try to differentiate with respect to p. It's ugly enough. Okay, so you're going to get 1 by p here, 1 by 1 minus p here, so you write it down. You will get this equation that np equals x1 plus xn by n. Okay, so I'm doing a lot of simplification in my head. I'm differentiating and then equating it to 0 and then simplifying to get this. So this is actually an expected result, right? The sample mean is n times p. Okay, so this is one equation. It should be good. But if you start differentiating with respect to n, you will get something that's really difficult to handle. Okay, so it's this log n choose n1. How are you going to start differentiating it? You can think about simplifying this in some ways. It does simplify. You can get it. You will get a you will get a slightly more complicated equation. Okay, so this becomes very complicated. I'll just leave it like that. Okay, so I welcome you to try it, but you won't get anything too simple. So there'll be some simplification, but it won't be all that nice. Okay, so to get to the answer here, it's a little bit more complicated. Okay, so I'm not even sure if how the answer will look at the end of the day. I've not really tried very hard to simplify it, but my guess is it's going to be a little bit more difficult than before. Okay, so maybe it'll come out to something interesting, but it's at least very complicated. Okay, so we saw quite a few examples, simple examples like Bernoulli, Poisson, exponential, normal, where sample moments ended up naturally being the answers. It was very nice to see. Then we saw slightly more complicated examples, uniform distributions, both discrete and continuous, and then also the simple discrete distribution, 1, 2, 3, P1, P2, P3, where ML and MME started giving different answers. Okay, very different answers. MME usually was not that great. ML ended up being always very good. Okay. And then these final type of examples where you have gamma and binomial, where simplification with ML is really hard. MME ends up being much simpler in that case, right? You're able to directly get something. Here in this case, it's a little bit more difficult. Okay, so you'll see all these kind of examples with other type of distributions as well. Okay, but the recipe is always the same for ML. Likelihood, throw away what's not necessary, take log, differentiate with respect to the parameters, and try and solve. You get your ML estimate. Okay, thank you very much.